Hello again, everyone. We're here at UNSW. We've just had a day of interesting research talks. Now at the final stage of our day of seminars, we're leaning into the reading seminar series components of the Australian Geometric PD seminar series. As you may be aware, we conducted a vote asking you which topic we should cover for this year in the seminar series, and the overwhelming majority of you suggested that we should do Yang-Mills theory, which is an interesting choice because I don't particularly know too much about Yang-Mills theory. So hopefully I'll be able to learn some of this with you over the coming year. So to introduce our topic to Yang-Mills theory this year, we've been fortunate to have 3 people volunteer to give 3 short talks on the subject, introductory concepts that will help us understand the topic as we move forwards, I suppose. The first of these speakers is going to be delivered to us by Stepan Hudecek from the University of Queensland, and he's going to be giving us a short talk on, I suppose, the basic definitions that we'll likely encounter as we go through Yang-Mills theory. So thank you. Take it away, Stepan.
Thank you very much, Tim, and thank you again for organizing this session in UNSW. It's been nice. All right, so as Tim mentioned, this talk is going to be very introductory, very basic, a lot of hand waving. It's like 20 minutes, so ask questions, and then I'm going to try to give you the feeling what diagonals are like, and I'm going to try to get the actual equations and mention some applications, just to motivate our studies. Yeah, and as always, don't hesitate, ask me any questions. I don't write particularly nicely, so just read only that in this same voice. Okay. It's fine, I can start. Okay, so this is something, right? So I guess I'm gonna try to motivate it first from some kind of mathematical point of view. So I believe you've all seen the question, given a Riemannian manifold, or let's say differential manifold, what's the best metric on our manifold, right? And there's all sorts of nice geometry you can get out of this question. For example, the Einstein equation that we've seen today, but you don't always have Einstein metrics, and all sorts of other questions, which is very nice, but we don't always have the nicest method. So the idea is the following. So given a Riemannian metric G, we know that we always have the so-called Levi-Civita connection, the connection which is torsion-free and which is compatible with the Riemannian metric. So we can kind of flip the question on its head and ask ourselves, well, if we don't know what's the best metric, maybe we can ask what's the best connection. And this already kind of enlarges our domain, because, as you probably know, not every connection is given by a metric, right? Not every connection is Levi-Civita connection for some metric. The first obvious obstruction is the torsion freeness. If our connection has torsion, it cannot be Levi-Civita from someone else. The second, maybe not so obvious obstruction, is the holonomy, which I'm not going to mention anymore today, but basically, if the holonomy is not compact, it doesn't sit inside OM, it cannot be compatible with some metric, because every connection coming from metric must have a holonomy inside OM. And it's actually only 2 obstructions. If these 2 conditions are specified, it's actually Levi-Civita from some metric. Okay, so we're going to try to find some connection, possibly the best one. And this is kind of I think at the heart of motivation for Yang-Mills theory. Okay. Now, another kind of crossroads we end up in the Yang-Mills theory is where our connections live. So there are 2 possible ways to approach this. First is connections on vector bundle. It's usually something like this, where typical fiber is a vector space. And another possible approach is something like a principal bundle, which Ramiro already mentioned today. And that's, again, a bundle, which when I say bundle, those of us who know, think about something like product with a Lie group or with a vector space, depending on which stuff we are, which somehow globally isn't a product. So there can be some twists globally. I mean, like the most basic example is if we consider S1 times Z2, two sucrose above each other, nothing special there, but we can kind of S1 times some twisted product, which is going to look like figure 8, which again locally still looks like a product, but now it's topologically completely different, right? It's, for example, it's one component, not two components, and so on. So these twists are exactly what distinguishes bundles from products. I don't have to. We're probably gonna get into it more into the semester. Right now, when I say bundle, just think of something which locally looks like a product. Okay. Okay, and as I mentioned, there are two formalisms: the vector bundle formalism, the principal bundle formalism. I'm gonna use the principal bundle one. I think it's much more prevalent in the papers, at least what I've seen. And also, I like it more, which is the reason as well. And it's actually a bit more general. Okay, so what's the setup? We have a principal G bundle. I guess one more node. The base manifold M is going to be always compact. And this is G principal bundle, where G is again compact. Okay, so the typical fiber is a compact Lie. Okay, I'm fine with that. So now we need to introduce the notion of a connection. We want to choose the best connection, so we need to know what we are actually talking about. And a connection is something which Hammer mentioned in his talk as well. So when we look at the tangent space of our total space, it actually naturally splits as naturally splits. That's their formation. We have this part of our tangent space called a vertical vector bundle, which is kernel of our this projection is called Pi. Basically, all directions in the fiber. So if you imagine like this is the underlying manifold, let's say we have a circle group at each point. So the vectors that are tangents to our group and the fiber are living in this vertical bundle. Sorry. Okay. So what is a connection? The connection is actually a choice of a horizontal bundle, which is a complement to this vertical one. Really, connection is just the splitting of the tangent bundle upstairs. Somehow, if you know which one is horizontal, you can transfer the vectors everywhere, and you can have covariant derivatives and all that stuff, fun stuff. So we need to describe this HP, the horizontal bundle. Right? So there are a number of equivalent ways we can describe them. For purpose of this talk, I'm going to use the description using one forms. So what we have A, one form on a tangent bundle on the total space P, which actually values in the Lie algebra G. And then the horizontal distribution is kernel of our A. Now, there are two conditions which we're going to put on A, something called G equivariancy, and also that it must reproduce action vector fields. But I have only 20 minutes, so just imagine some properties of our A. It's not any one form, it's one form with some two special properties. I think I'm going to mention the properties probably right in the first talk, but for now, it's just a special type of one form whose kernel gives us complement to the vertical distribution.
So, Stepan, in particular, are you saying that a connection is not just a choice of horizontal distribution, there are extra conditions you need.
No, it is.
But it needs to be G
Yeah.
invariant. That's the only extra
Yeah,
condition.
the only condition exactly, Emerson, is a G invariancy, which means if I move under the action of the group, it's still the same distribution, right?
Yep.
So I'm just saying that there are conditions on A such that it gives me a nice complement.
So if you wanted to avoid using A to define a connection, you would just say G invariant choice of horizontal subspace. There we
A complement to the vertical distribution.
Yeah.
Yeah, that's enough. But if you want to actually compete with something, competing with distribution is horrible.
So you need the A.
Yeah, you need to do anything. And actually, you can actually get much worse in the future because we actually want to do computations mainly on the M. So we want to somehow pull it down, which it turns out it cannot do globally, and we need to do some local something, and that leads to gauge fixing and all that gauge theory business, which we're gonna get later. Oh yeah, thanks for the question. Okay. Any more questions? Okay. So hopefully this is good at the connection. One of the nice features of having a connection, which is, I think, somehow quite essential to doing a gauge theory if we want to look at the global picture and the local picture as well, is the correspondence between horizontal forms. So horizontal forms are just the forms that ignore the vertical direction. If I put there any vector from vertical, it's gonna give it 0. So it's considering only vectors in the horizontal direction, right? And because of our A,
Are these one forms or
yeah,
Okay.
anything. Just again,
so
the
you
correspondence
when,
doesn't matter.
so when you put only one of the components vertical, then the whole thing vanishes?
Yes.
Or do they all need to be vertical?
Just one component.
One
now.
vertical.
If you do basically what's it called? If you insert there any vector which is vertical, it's gonna give 0. Not in a product, maybe IV.
Yeah.
In product as well. Yeah. So what we can do now, we have this one-to-one correspondence between horizontal forms above. By above, I mean in the total space, and the same forms below, just on the base space. Very important. And here again, sorry, just sweeping it under the rug. Now the values are actually not in the Lie algebra; they are actually in some vector bundle, where typical fiber is the algebra. So kind of, if we move down to the base space, we need to respect the twisting that's introduced in our bundle. But you can think of it again locally. It's again vector valued K form or star form. Okay. So the FG I'm writing here just to be formally correct. Really, you can just put there just the algebra G. It works almost fine. On trivial bundles, it works as well. It's the same in trivial bundles. Right? So this is important correspondence. It's gonna be important later. Okay. Now we would like to have some value to our connection, right? Because we want to pick best connection. So we want some value given to each of our connections, so we can pick the best one, right? So ideally, some functional that eats a connection and give us a number, right? So there is one very natural choice, and that is the curvature of our connection. Again, the definitions of a curvature in the principle bundle setup are, I believe, at least 5 equivalent definitions. I'm going to use one, and maybe we're going to discuss that again further. So the definition I'm going to use, which is not very intuitive, but is this is curvature A for connection A, And it's given by the strange dA applied to A. So what is dA? dA is actually exterior covariant differential. It's quite a big name, but it's I mean, to understand it, it's I think quite difficult. But to give you a rough idea, what does dA do? dA form, let's say, values in the algebra and produces horizontal form. And how does it do that? Well, if our form is, let's say, alpha, what we're gonna get is dA alpha. The dA alpha evaluated at, let's say, x1 to xn is just by a definition the usual differential for forms. But then for each vector, we're gonna apply the horizontal projection. Basically, each vector is gonna project to our horizontal distribution, and then we're gonna feed it to the differential. Right? Make sense? So very naturally, our connection, our curvature right here. Here is already a two form, which is horizontal. Right? Because I just mentioned that the exterior covariant differential produces horizontal forms. Right? So we can apply, and we're going to get horizontal form. Okay. Now, if I'm going to write this a bit more in our language, let's say, differently, this is just a section of, second exterior power cotangent bundle, right? That's exactly what forms are. Tensored with the other, right? So far, so good. Okay. So, okay. Now we're gonna use our correspondence. And we're gonna actually get two form on the base manifold with the values some adjoint one. Which in this language is section of a second exterior power tensor with this adjoint one. Again, think the algebra in the second slot.
M rather than P.
Ah, yes, sorry, thanks. Yeah. Thank you. And now this is very good because now we have form on our base manifold where we have metric. So we know how to measure the first part, right? When we have a metric on our manifold, we can measure how big two forms are. It's nice. What we need is somehow to measure in the second coordinate, somehow a metric in the algebra. And again, there's very natural choice because I mentioned we have a compact group, so we can just take filling form in the second slot, no problem with that. And now we have enough to define finally the Yang-Mills functional. So the Yang-Mills functional, it's a connection and produces an integral over all of M. As I mentioned, M is compact in our case, so this is well defined. And it takes the value of curvature or the norm of our curvature with respect to the metric I just mentioned. That's it. That's the Yang-Mills function. All right. So now all we need to do is we're just gonna look for extremes, find the best connection, and we are done. Right? That's pretty much it. except it's quite difficult. So I don't know. Yeah, I don't have much time, so I'm gonna just write what the first variation is because I'm not gonna compute it. Don't have much time. So the first variation is actually a star, the adjoint with respect to this G tensor B product to our FA is equals to 0. Kind of pops out naturally with the computation. It's not lengthy computation and just don't have much time. Right? And now there is a bunch of problems. So first remark.
So you mean these are the critical points? This
Yeah.
is the only Lagrange equations.
Yeah, these are Euler Lagrange equations for this functional above. Also, one thing which is quite easy is that, as in Hodge theory, the codifferential or the adjoint to our differential is again just star a star, where star is the Hodge star operator. So we can rewrite the equations in the following form. And this is what you usually see when you look for Yang-Mills equations. Okay. Couple nodes. So first node right here, the A above the differential kind of indicates and we've seen it before, the differential depends on our choice of connections. Hence, the system is nonlinear. Because whenever we change our distribution, the differential changes behavior. Is not a linear system. First bad thing. Another bad thing. Again, I don't have much time to explain in full detail, but maybe you know that on a Lie group you can do the, let's say, left action, and the Lie group's gonna kind of translate, like rotate or something. And you can do that on a principal bundle as well, except at each slice, at each fiber, you can multiply by a different G. Right? You can think of it like if you have a torus, you can think of as S1 times S1 bundle over S1. You can rotate the circles by different amounts, and it's still, this is a smooth operation. You're gonna change the torus into torus, but the structure of the bundle is gonna change, right? But the bad news is our integral kind of doesn't care about the position of the connection within the fiber. So any such transformation doesn't change the Yang-Mills functional. And this is kind of hand wavy showing you, this is what's called a gauge group. It's actually any principal bundle map that this. Any principal bundle map that preserves the fibers. It's an element of a gauge group of P. And unfortunately, as you imagine, and at each point of the base, you can choose different G smoothly. This gauge group is infinite dimensional, and it doesn't change the functional, right? Which means we have a big kernel in our equation, which means it's not elliptic. Another point why it's quite difficult. So this A means not linear, and the not linear is not so bad because we will see probably in the semester it's something like quadratic-ish, so it's not like that bad, but nevertheless it's not linear. And the gauge group is infinite dimensional, which implies Yang-Mills equations. Yang-Mills equations are okay. So good. I have like 3 minutes. Is everything good? Okay, so maybe just a few final remarks. s- First important special case. If n is 4-dimensional, which I think is gonna Rhuaidi talk about in a minute, we can find very special solutions to our Yang-Mills equations, and those are because Hodge star goes from K forms to n minus K forms. Our curvature is two form, so in a four manifold, the Hodge star goes from two forms to two forms. So we can actually look for connections whose curvature is so-called self-adjoint, actually plus or minus self-adjoint. And these are called self-dual and anti-self-dual connections, which their spaces play a huge role in the four-dimensional topology. We're gonna hear in a few minutes. It is one special case. Another fun special case, I wanted to do it in a bit more detail, but I won't. So if we choose our group to be U1, it's abelian. And what happens is that the differential becomes the usual differential. If you write down the explicit formulas, it becomes clear that it vanishes. I didn't do that, so it may seem like a magic, but the nonlinear part is going to disappear. So in the case of U1, we're essentially looking for connections with harmonic curvature, right? I'm saying harmonic, and I'm writing just one equation. What I didn't mention, I should have. This condition always holds. This is called Bianchi identity. You know them from Riemannian geometry, and they hold even if I write here this A. Okay. Yeah. Final remarks. You may know that if you are looking for a harmonic form, harmonic two form, let's say on a R4, there are 6 coordinates we are looking for, right? Because it's two form in 4 dimensions. And with correct notation, it can actually be shown that the harmonic equations are the same thing as Maxwell equations. So this kind of gives you basically electromagnetism. If the group is U1 and we are in R4, and we are using Minkowski metric instead of the usual one. And you may say, okay, well, that's just coincidence because the A disappeared and we are looking for harmonic forms. You are kind of right, but not totally, because if you're gonna look at actually SU2, this equations, set of equations are there. Again, in R4 with the appropriate notation and appropriate changes of the metric, this gives you actually weak nuclear force in physics. If I put a SU3, you're gonna get strong nuclear force. So it's really essential tool in physics. And it's actually the Yang-Mills function is part of the Lagrangian given for standard model. It's really important tool in physics, and it's used for finding new new physics, let's say. And I think it's also obvious from the fact that both Yang and Mills were physicists. This theory is somehow coming from physics. This is the usual motivation. You kind of twist and give you a mathematical motivation for finding the best connection, but this is the thing you usually get. And with that, I guess I'm out of time. Thank you for that. Any questions?
Yes, thank you for that, Stepan. Does anyone have any comments or questions?
Just quick comment, but I mean, is Rhuaidi going to talk about? Are you going to talk about Donaldson stuff?
Yeah, I usually do, but
No, I mean, because I think even though they come from physics, like I guess there's also mathematical motivation, right? Because these equations played a big role in four manifold topology. Like some people had the idea of given a fixed four manifold, counting how many solutions you have or these or related equations, and that turns out to be an invariant, and you can compute it, and somehow that leads to groundbreaking results in four manifold topology in the 80s, I guess.
Let's thank Stepan again. Have a quick chat amongst yourselves for a couple of minutes while we transfer over to the next speaker. We're going to continue discussing Young Health theory in particular. Our next speaker is going to be Rhuaidi Burke from the University of Queensland. We're going to be talking about intersection forms and homotopy classification for manifolds. Thank you, Rhuaidi.
Are you recording it?
Yes, I think it's.
Yeah.
Yes, I think it's still recording. Yep.
All right, Tim. Thanks for the introduction. Thanks to the organisers for inviting me to speak today. What it says on the tin, right? Intersection forms and homotopy classification for manifolds. So I'll start with just some like motivating ideas. So I realized that this is mostly like geometry and PDE people. This is going to be quite a topological talk, but if I say things that you're not familiar with, please feel free to ask. But I think it should be all fairly low level stuff. But just to start, like very motivational sort of ideas. So of course, in topology, we want to classify manifolds. We want to make a list of all different types, right? And in low dimensions, so three and lower, this is quite a geometric, concept, or is a geometric sort of thing. So by which I mean, right? So for example, surfaces, compact oriented surfaces, you can classify by their genus. In 3 dimensions, you've got first geometrization program. In dimensions 5 and higher, I think you've got surgery theory, gives you classification results, and everything becomes a bit more like algebraic. And then in the middle, like dimension 4 is this weird place where everything just sort of falls apart. So without saying anything too specific, I'll just say that the fact that 2 plus 2 equals 4 is it's a real like spanner in the works. And I mean, dimension 4 is a crazy place. It's the first dimension where we get a split between the topological and differentiable categories. So the first example, right, is for any dimension other than 4, boring old Euclidean space has got a unique smooth structure, right? And then R4 comes along and you don't just have another one or a few or countably many, or you've got a continuum, right, of distinct smooth structures. So I mean, if that doesn't give you nightmares, I don't know what will. Big open problems, right, in full manifold topology are, like, does S4 admit these so-called exotic structures? But even, like other small things like CP2, like complex projective plane, S2 cross S2, right, completely open. And so these are sort of like the big problems that full manifold topology tend to think about. So another thing, right, thing to mention is that any finitely presented group can be the fundamental group of a full manifold, and it's a classical result that determining whether 2 finitely presented groups are isomorphic is algorithmically undecidable. So as a consequence, we can never classify full manifolds in their entirety. There's no list, right, of all the different kinds of full manifold that we can sit down and enumerate, right? So then you have to start thinking, well, what can we do, right? So what if we then restrict to, say, simply connected full manifolds, right? Just as a starting point. And as it turns out, even just doing this gives us plenty to get on with. So if we restrict to simply connected, then if we just start even thinking about, what's going on at the homological level for invariance, the only interesting thing that's happening is in H2. Okay, and so with this in mind, we can introduce what's called the intersection form. So given a closed-oriented simply connected full manifold, the intersection form is a symmetric bilinear form on H2, which sort of just naturally falls out of the cut product on cohomology. So this X hit, this bracket X is you can think of as just being a choice of orientation for X. I mean, but like what does this mean? I don't know. So this is very algebraic. This is a geometric PDE seminar. PDEs frighten me, but we can at least try and make things a bit more geometric. So let's do it. So by Hurwitz's theorem, the fact that we're simply connected then sort of gives us that H2 is isomorphic to Pi2. So what does that mean? It means that all our homology classes can be represented by maps from S2 into X. And, you know, you can turn these maps so that the only place, so in general, right, this might be an immersed sphere, right? And the only place where it fails to be embedded is just at finitely many transverse double points. And double points we can eliminate these guys at the price of increasing the genus from a sphere to something of higher genus. Like diagrammatically, you could think of, so this is like two complex planes meeting at the origin, right? The only point where they intersect is at the origin. You can perturb this so that, you know, so they split off each other. And if you think about, like, say the Hopf vibration, so the trace, so imagine like the three spheres sort of sitting here, then the trace of these planes, right, in the three sphere are two interlinking circles, which I've drawn up here. And so there's like what do we do in this perturbation? It's basically like this is sort of in the four ball bounded by S3. So in the perturbation, I'm basically replacing this sheet, right, by this annular region, right? So you're sort of like sticking a tube, sort of to get rid of the singularity. So you wind up increasing the genus. So the point though is that if I've got an embedding from an oriented surface into X, you can even just think about like the induced map of homology, right? So this surface has got its own fundamental class. So then the induced map of homology gives me a class in H2 of the right, and so, you know, like here's a picture of what. So what you really need to understand, right, the fact that in 4 dimensions, right, planes and surfaces, if they intersect, they only intersect in points, right? And so this is a very accurate picture, right, in the sense that where do we get a point of intersection? You only get a point of intersection where, so if I color my 4th dimension, right, this is my coordinate, then the only point where they intersect, right, is if all my spatial coordinates line up and my color, right, is the same, right? So the only place where these things have the same spatial coordinates and color is just this one point there. Okay, so this is the picture you should maybe have in mind. Right, okay, so yeah, like I said, two surfaces intersect in points. So then what can we do? So for each of these intersection points, you can assign a plus or minus 1. So like take the tangent space at each of these points, right? Stick them together, the bases of these tangent spaces to give you a basis of tangent space of the whole form manifold, right? And then just say it's plus or minus 1 according to whether the orientation, right, of this concatenated tangent space has the same orientation as the ambient form manifold. So with this in mind, right, the intersection form, we can rephrase it like this, and it really does what it says on the tin, right? It's counting intersection points of the surfaces, which represent, now I've written it as homology classes. So technically you'd need to do some work to show that this is the same as as the cohomological definition, but that's just pushing things around with Poincare duality, and you can write some stuff out in local coordinates, wedge product, right, 2 forms. Like you can turn everything back into Durand cohomology and you'll see that it all works out. Okay, so it really is, so this intersection form is really counting intersection points of classes representing these 2 cycles. Okay, so just some facts, right? So this form it's non-degenerate over the integers, hence it's invertible. It's unimodular. So if you represent this thing as a matrix, that just means it's got determinant plus or minus 1. You can compute a bunch of algebraic invariants that, you know, the sort of usual things that you think about just associated to, you know, symmetric bilinear forms, right? So take the rank, that's just the rank of your second homology. Signature, so that's like diagonalize it over R, and then difference of positive and negative eigenvalues, you know, whether it's positive definite, negative definite, indefinite, that sort of thing. Maybe the only one that might be new that you might not, I don't know, right? But if maybe you haven't seen before, is this parity thing. So we call the form even if for all the classes it's 0 and then odd otherwise. I'm not going to say much more about this stuff, but just, you know, these are some of the things that will come up maybe if we, you know, go into like nonsense papers and stuff. Okay, so this is all very well and all. Well, yeah. So let's think of it just a dumb toy example. Just halve all the dimensions. So now H1 and into a 2 manifold. So if we just think about the torus, right, its H1 is generated by these curves alpha and beta here. So how do I need to compute then self-intersections? Well, I want all my self-intersections to be transverse, right? So what do? Well, I just take like a parallel push off of this curve, for example. Homologically or homotopically, alpha dash is the same thing as alpha, so that's fine. And now all my intersections are transverse. So I just count how many times does this thing intersect this thing. Clearly it doesn't, so it's 0. Ditto with beta. And then alpha and beta, like obviously intersect in this single point. And once you orient everything, let's say that that's fine. So you could then say the intersection form of the torus is this. Let's look at a 4-dimensional example. So basically the simplest, simply connected compact 4-manifold that isn't a sphere is the complex projected plane. This is like the space of all lines through the origin in C3, non-zero, right? So usually in these projective spaces, you work in homogeneous coordinates. So this is just like, imagine your regular X, Y, Z triple. So these are elements of C3. But I'm just considering these things up to this equivalence relation. So up to scalar multiples, right? And now notice that like the image of a hyperplane through the origin under this quotient map, okay, is now just, all right, so set Z equal to 0, it's now something like that. But if I just forget about that third coordinate, well, now I've got something where, all right, if you write down all the definitions and local coordinates and what have you, you see that this thing just bring all the numbers down as you need, right, is now a point in CP1. CP1 is just S2 with a complex structure on it. So there's a copy of S2, right, sitting inside CP2, and this is what generates our second homology. And now put like your projective art caps on, right, or just write things out analytically, I guess. Any two projective lines are going to meet at a point. Okay, so take a CP1 and or again, parallel push off, right? So these things intersect at a point. So the intersection, and this is all you've got, right? It's just this S2 generating H2. So the intersection form of CP2 is just the 1-by-1 matrix plus 1, right? So that's what I mean. It's really quite simple. S2 cross S2, right? It's pretty much the same kind of idea as like the two torus, right? Except now everything's so think about that if you like. Okay, so this is all very well and all, but you might be thinking, okay, is this actually an interesting thing to think about, right? So yes, as it turns out, so the first thing historically, I guess, is this theorem due to Whitehead. I want to talk about this a little bit more later on, which said that in fact, if I've got two closed simply connected topological form manifolds, then they're homotopy equivalent if and only if their intersection forms are isomorphic over Z. And then a more recent result due to Friedman says that in fact, any symmetric unimodular bilinear form, there is a simply connected closed topological form manifold which has the intersection form that given form. And then shortly thereafter, so, and this is sort of, I guess, one of the theorems that we are interested in the seminar this year is due to Donaldson that says if we, okay, so I've phrased it here saying the only symmetric unimodular, these symmetric unimodular bilinear forms, so copies of +1 and -1, are the only definite forms that can be realized as intersection forms of a smooth closed form manifold. So now this is actually saying something about the smooth structure. And now, so a corollary of this, like putting these two together, and well, like technically thing due to serve about other indefinite forms, but anyway, let's say putting these two things together, we now actually have that if we restrict our attention to smooth form manifolds, then smooth simply connected form manifolds are homeomorphic, right? If and only if their intersection forms are isomorphic. Okay, so now we actually have this. Actually gives us a classification of another corollary of this is that there exists topological form manifolds which don't admit any smooth structures, and for people that, if you only ever think about things with smooth structures, you know, doing geometry and that, this is again, nightmare fuel, right? Kind of weird to think about that such a thing could exist. But anyway, so yes, so these are sort of the big things to play here. Let me quickly sketch a proof for this theorem of Whitehead's. And maybe also this gives you an idea of the level of, you know, machinery involved, in the sense that, like, I can come along and give you the sketch of Whitehead's proof, Whitehead's theorem, you know, in 10 minutes or so. But as we sort of go up from homotopy equivalence to homeomorphism to something about smooth structures, it becomes, you know, a seminar's worth of stuff to think about, right? Okay, so how can we at least start with homotopy equivalence? So the proof goes like this. So remember, we said Hurwitz's theorem gives us an isomorphism between H2 and pi2. And this isomorphism can be explicitly realized by a map of this form. So this is just a wedge. So this is just wedge sum. I think everyone knows wedge sum, right? But like, so just imagine these are all just two spheres that all like just hit at a single point, right? Into X. And this induces an isomorphism on all our homology except for the fourth. And so what I can do is then, like, I can cut out a small four-ball from X, and it's, you know, you can easily set up this map so that it avoids the four-ball that you cut out. And if I do that, then that annihilates H4. And now this induces an isomorphism on all my homology groups, and in turn the associated homotopy groups. And so then by, like, Whitehead's other probably well-known big theorem, right? This says that if I've got such a map which induces this kind of isomorphism, then in fact I actually get a homotopy equivalence. Okay, so X without a four-ball is homotopy equivalent to a wedge sum of two spheres. And so then what can I do? Well, I can recover X just by sticking back in the four-ball. Okay, and I've got to do this via some map from the boundary four-ball into this wedge sum. So then what does that mean? Okay, so this is S3, right? So a map from S3 into something. So the homotopy type of X then is determined by the homotopy class of this map phi. So everything turns back into understanding homotopy groups here. So we have to understand this homotopy group here. And so the claim, right, is that phi, this map phi, is determined by the intersection form of the format fault. How can we see this? So start by just pick a point for each of the spheres in your in that wedge sum of two spheres. Okay, and so now, right, the pre-image of that point, of one of those points, is going to be an embedded circle in S3. Okay, and again, just think like, think Hopf vibration here, right? Which, you know, sort of gives you this map from S1, S3 is parted by circles, and you get a point in S2 for each of those circles, right? So just think of Hopf vibrations. But also, right now, I've got an arbitrary embedding of a circle into the into a three-dimensional space. So this circle can become knotted, right? So I've really got a knot. And so if I do this for each of the points in all my two spheres, I get a collection of knots, which we call a link, right? So these things could be linking with each other, or off floating on the road, whatever. So this is sort of the picture of here. So this is my wedge sum of S2s. Here are my points, right? For each point, I get a knot. Okay. But this isn't all I get, right? So I actually get some additional structure just naturally occurring. So for each component of my link, I can embed its normal bundle as a sub-bundle of the tangent bundle of S3. And now by assuming that phi is transverse to each of my points, again, this is just like perturbing things to be nice, right? And we can assume that phi is differentiable, at least in a neighborhood of my component. So then this means that the differential of phi restricts to a map from the tangent bundle of my link component to the tangent space on S2, the associated S2, in such a way that it's an isomorphism on the fibers. Right? I mean, this thing is just right R2, right? So really, what have I got? I've got a trivialization of the normal bundle of this not. Okay, and a trivialization, if you've got a knot and a trivialization of its normal bundle, this is what's usually called a framing. Okay, you could, even just picture it as like, okay, I've got my tangent space TPS2, right, and I can pull back the associated structure. I mean, really, maybe this is a more accurate picture, right? Because things could be twisting around upstairs. Okay. So associated to this link is some numerical data I can compute. So for example, I could count the number of times any two link components link. Right? This is called the linking number. And I also have a self-linking number for each of my components, which is induced by the framing. And this is just counting like the number of twists in my normal bundle. Okay, and I can stick all these numbers into a matrix, right, which we call the linking matrix itself. And so now, right, what does this mean? Well, okay, so now what I claim that this linking matrix is going to be the intersection form of my form manifold. How can we see that? So we want to show that the linking matrix is my intersection. So how can I see that? So for each of my link components in S3, could just choose some surface in the four-ball, right, which has that component as its boundary. Okay, and so now what's the key observation to make? The key observation to make is that for any two of my link components, then the linking numbers downstairs, right, the linking numbers of my link components are going to coincide exactly with the intersection numbers of these associated surfaces. Okay, so you can imagine, so downstairs, right, again, I mean, in this picture, right, most of Sj, most of Lj is sort of like coming out in the fourth dimension, right? And so, I mean, these things come out and link, right? And then the associated surfaces, that's exactly where I'm going to get an intersection of the associated surfaces. Okay, so what do I have? It means that so when I'm considering the homotopy type of my form manifold, when I stick back in that four ball, what's going to happen is like each of my knot components, right? You can think of as getting like that boundary is going to get sent down to the point downstairs in that wedge sum. Right? What does that do? Okay, so now I've got a closed surface, right? I said that, so we observed that the intersection numbers of those surfaces is going to give me at least part of the intersection form, right? So, I mean, so really I should say the intersections of these closed surfaces. But then the thing to keep in mind is like, I mean, maybe I haven't captured everything, maybe there's other stuff that could be going on. So how can you see that the intersections of these surfaces give me everything? So what would suffice, right, is to show that actually these surfaces give me a basis for my second homology. How can you see this? So remember we said that H2 was originally generated by this wedge sum of two spheres. So for for S2I, right? Si intersects that sphere exactly once. And the fact that my intersection form is unimodular or invertible over Z then implies that actually those Si give me a dual basis, right? And again, how can you see this? Well, start with the basis here, push everything forward by Poincare duality to get a dual basis, and then you can sort of bring everything back. Anyway, I'll say that, like, I mean, if it's not clear why this is true, it's just an exercise in Poincare duality. Okay, so I've got this. This gives me the entire intersection form. Technically, right, I didn't show that the homotopy class of phi was determined by the linking matrix, but I mean, it's a 20-minute talk and I'm pretty much at time now. So maybe that's for the best, right? And I'll just say that it's something to do with framed coordinates, right? Framed coordinates. So something called on-track construction. But it's not too difficult to do this, but yeah, sort of beyond the scope of what we want to do. So yeah, hopefully that gives you then a gist, right, of Whitehead's proof. I'll leave that.
Thank you, Rhuaidi, for taking us through some of the fascinating things that can happen in four-dimensional topology. Does anyone have any comments or questions for our speaker?
Hopefully, is anyone still with me? I remind you, lose everyone.
I've just got a quick one. So the stuff that you were doing there with the intersection forms, does that, does the exotic R4s follow from anything that you've done here?
No, not really. How can you construct an exotic R4? And no, it's the short answer. Maybe something I didn't mention, I guess, because I think about this all the time, but maybe I should mention it here, is that, so just with Donaldson's thing, right? So if you're smooth, definite, then all you get are these. And so remember, like, these are precisely the intersection forms of CP2 and like CP2 with its opposite orientation, right? So really saying if you're definite and smooth and closed and all the other adjectives, right, then all you could be is a connect sum of CP2s or CP2 bars. So it really, sort of restricts, because in theory, right, how many definite symmetric unimodular bilinear forms are there? A lot, right? There's a lot. Google it. But so in principle, before this, you could think, okay, well, how many? I need to think about definite forms, but in fact, no, you don't, because if you're definite, then what it could be is a bunch of CP2s. Anyway, that's just something.
Let's thank Rhuaidi again.
Thank you for inviting me. And I received email saying everybody wants to study on Earth. I thought maybe people here are eye for the Millennium Prize. This is like a mass conjecture, mass type conjecture Young theory. Right? So I know we have from different background. Hopefully my talk gives some idea what we want to discuss. And thanks for the previous two speakers. They are very for me, so I'm respect to. So we pick up as we already know that we started with four manifold is the many metric. Then we look at the principal bundle, principal G bundle, and G is a compact group. Maybe say for simplicity, G is SU2. And SO3 is fine, but this is probably the simplest long bearing group. And we know that the U1, which is the Maxwell theory. And then what we're going to look at is, so this will be the space of connections. So we're going to look at it just put some topology, so L22 or W22 connections on this bundle P. And so this is fine. It's fine. Here, but it's a manifold, even original, and it's affine that is modeled on already like tangent space. So these sections of locally in the actual value will form with transition function. So which is a joint bundle. So a joint bundle by a joint action of group on the atom, based on metrics and just magic conjugation.
Go to the next page. Next page.
Just scroll down. Your finger.
Yeah. Okay. And then we also have gauge group. So we have this very large affinity. This gauge group will be not G. So this essentially is a sections, or maybe I take a section which is L2, 3. So this is gauge group, which is by solving Lane theory, all these gauge group are these continuous sections. So these sections will be another associated bundle instead of conjugation action on the group set. You can see that the triple bundle may be non-trivial from more global section, but this associated joint bundle as twin sections. So this again, if you look at the rearguable part, rearguable of this gauge group, so this will be the omega zero of this. So we're going to call this little ABP. So this ABP value sections, functions. So, and then so we have this gauge group fraction. So now maybe I jump to this low remission of the Young-Mills function. And the Young-Mills function, which is gauge invariant. And this is a function on the space of connections. We take the curvature here, and we essentially take the L2 normal square. And if we want to using this SU2 or maybe LED group, we test for unit representation. So let's just take I think it's SU2, so with minus trace or with the chaining form. And then we have this star operator, then two forms. That is the L2 and then you can associate another, which is second chain class bundle. And this again, there will be some sign formation differently, using differently than just using I think it's done in Kohler-Hammer's book, which is different to the Friedel rule of your sign. So the second chain class of this principal bundle, you may think that it's SU2, and they just like take the rank 2 comes back from it. And this will be just a trace, and so of course this is manifold text. So this just so like a two-way here. And then you can see that if I already have a star operators on the two forms to with any associate any bundle value two forms, and the square is identity. So we can look at the positive and negative eigenspace and of this star operator. So and then that will be so now okay, we already know the Young-Mills equation. We just jump to that. We have this Young-Mills equation, which is they use different notation for the geometry. There's L2 norm there, so that's the curvature to 4. This is the Young-Mills equation. And also we know there is automatically the Yankee identity. So this is just the curvature to form is the vanishing. And then if we have this curvature, which is either positive or self-dual, this is what is plus or minus self-dual, minus or anti-self-dual. And then maybe we look at just a quick, we can rewrite this. So this essentially, we can write a curvature in terms of the positive part, self-dual part, anti-self-dual part. And then, of course, this is just this homogeneous composition. So we have these two, this selective of the field and this selective part of the square. And then this part, we write the negative part belongs to L2 sphere minus the positive. You can see that not every bundle admitter anti-self-view. So we have particular solutions. Okay, so we now that let's call this number k. Actually, this will be. Okay, so maybe before so this will be. So the C2, I think I forgot that it's 1/8 pi squared. So anyway, so this let's call this right. Maybe I just rewrite this. It's just that will here is the C2. And then, so let's call this are integers. So this, okay. And we know that this is can be written as negative part of the yeah, up to this. Okay. And so if k is positive, then our Young's function, which is will be greater than or equal to 8 pi k. Of course, that is this is always true. And with equality, okay. With equality holds for A is anti-self-dual or self-dual. It depends on whether k is positive or negative. Okay, let's say k is positive. And then Young's is always positive, function is always positive, so that means in this case, the only possible which is called this self-dual part. Okay, so now we have this, and then maybe I'm going to write it this way. So going to interpret this. We have a quotient that I gave you, and this is smooth except at reducible, where stabilizer reducible, you can think like the first one. A reducible where so let's take a SU2. So we have this, suppose we take a connection and then we have stabilizer. So this will be the element in the data such that we have this negative dimension 6A. And this either is always Z2, which I'm thinking SU2 case, or maybe is U1, or maybe the whole SU2. But the whole SU2 is only the triple connection, essentially for the triple one. So if your K is not 0, then this you don't have triple connection. So you may have everybody has this stabilized Z2 that you can ignore that. And then this reducible means let's just call this U1. And so you can just ignore the reducible parts, and then this will be a gap manifold. And then I can associate this with principal bundle over this irreducible parts. And then I look at the anti-self-view associate and self-view bundle. And this will be then our Young's function will be the anti-self-view. So this is the equation. So I will write. And then the modular space of anti-self-view Young's connection, sometimes for instance. And this is the sections which is that are already quoting it. So this and then if we use like the transversal theorem, so maybe generically, which is dynamic matrix. Dynamic matrix, and this section is transverse to the zero section. And if we know a little differential topology, if that is the case, at least the modular space, maybe I put this modular space, I denote with M, and there is a K, which is the second chain Newton number, second chain number. So then this modular space and irreducible part. So we're going to write, so this will be, so this is the irreducible part. So this will be a smooth manifold, essentially the infinite-dimensional implicit theorem of dimension. So dimension given by a TF index. So this we have 8k minus 3, 1 minus b1 for the number, and then plus b2 plus the second self-view part. So this is b2 plus or minus the dimension of the self-view and self-view forms. And so this is by TF index 0. So let's just take a particular case. So k is 0 and pi1 is 0. So let's take the particular p1 is 0. And let's also use the intersection form is negative definite. So I just use this. So that means p2 plus is 0. And then, so that is essentially, we look at the irreducible part of instance 1 modular space. This is 5-dimensional. So what is the modular space for the next page?
Stop recording.
Just the third unnamed document.
Okay, clear. Okay, so now the modular space is 5-dimensional. So then here we have to borrow. So first of all, is this Rhuaidi? If the modular space is non-empty, and this is laid work by tops. So these tops, what is called the function theorem or graphing theorem. So this is same as only for, so this is for any. Okay. What tops did is we can essentially can plant instant K means C2 this connection S4. But if we don't know what is the higher K, at least for K is 1, there will Polyakov that standard solution, which is 5-dimensional. And then we can plug this onto any closed format. And so essentially, goes with X4, topologically, you give a smooth connection path, just you cut a ball and fill in other ball, or it's something in the ball in the end of X4. And then depending on which instant you're going to, so essentially maybe I draw with this S4, and here you got some any points. You can look at a small ball, and then we think we can essentially like blow up that. We can stretch this connection. This is around the S3, another ball with the boundary S3, and then this is S4. You can see essentially put any just put some, let's put some standard K1, some instant here, and then depend on how small this ball is, like curvature is concentrated on this. Of course, this is glued by approximate ASP connection solutions, and then the perturbation to get to the solution. But this is already the consolidated, the innovation is subjective. Okay, so this means it's empty. And then there is issue of orientation. That can be done visually with another family index theory of a single. But the most important thing is the Burke compactness. So
Sorry, when you say orientation, are we talking about the moduli space?
yes, orientation of model space. Essentially, the tangent bundle, if the tangent bundle, this is origin. And again, then this tangent bundle, essentially, if you look at the tangent space, at each tangent point, this is you look at this is essentially the kernel of the linearization operator of the ASD connection plus gauge fixing. So then that is instead of calculate the dimension, you calculate the vector space. So this will be a family of index theorem for some orientation from K-root class. So this is another you can either in this case something to do with SU2 in this particular symmetry there. This is always also in 4 dimension. Essentially, family theory, you look at the W1 like a vector on. And so this is like is at least it is guaranteed, right? Not. And the compactness where the probably some the work coming. And so essentially you look at the sequence of ASP connections, and then whether these are ASPs in representing these class, and whether you have a limit. And turned out you could have like a runaway, energy runaway in any this two poles there. The energy can run away at the infinite or maybe concentrate at the points and go up. So this is, it turned out can of course this I use K here. And this is you have to remove these points, some points. And then of course you could do it either you can convergent in certain measure. And this measure instead of L norm, just like in this converge to measure and plus 1 to p, and then we have some positive integer here, and then we have delta x. All right, and then go there. And each of these, so if k is 1, then this modular space, okay, so you have maybe I should modular space is. So now I'm going to look at the k is 1, and we have to compactify by adding. So I didn't state the Bloomberg theorem. The Bloomberg have 2 theorems. One is a small curvature, and then put this in certain gauge called Bloomberg gauge. The other is removal singularity theorem, and then in a way which is the inverse of the TOPS result, which is TOPS you can graph the instant for S4 to edit x minus x. On the other hand, if you have sequence, the sequence could have a limit which is doubling of instant on S4. And so this can think that this is the inverse of TOPS theorem. And so now you can compactify by adding just 1 point. So and then this is nothing but just the k is 1, and you adding the points just the x, because k is 1. And maybe I should say that there is so there is a so-called the Bloomberg removal singularity theorem. Essentially, you have a connection, which ASP connection, which you have certain property on this, you can extend it to a different bundle. So then you will get a bundle, essentially this A infinity. So will be what is. So now I'm going to put the gate information. So this will be from one space of different K. And it's K prime. So K prime, which essentially is the K minus all these I from 1 to P and I. So you can see that if K is 1, I'm labeling this bundle, I'm city connected, I'm labeling this bundle by just the C2. And then, so it just depends where you put the points, where the points are. Okay, so, and so this gives us what is the, okay, so maybe I just, so we have this instant and order space of the one, and then there are some reducibles. The reducibles, these are 5-dimensional. 5-dimensional, and then a bunch of reducibles. And reducible, it turned out it is always CP2, different orientation, and you have to do the opposite orientation. So this is a cone over CP2, so that's the reducible, where the U1 acts from. And then here is 5-dimensional, just put back to X. And the top result say that this corner structure, you can invade this. So you have this, depending on the size, we glue the instant to X, so there will be some way of either strength end, whole on the end, we won't go over T. So there is common structure, and you can see that this gives us a coordinate of X with, so here there will be B2 plus is 0, so it's just B2 minus, B2 is equal to B2 minus. So will be C2 with opposite orientation. So that, and then that this is how the is, so now this is writing is -1, that is diagonalizable. Okay, so just quicker. So now if you want, so that is diagonalization theorem. Of course, there is application. You could look at E8 is standard with 8x8 intersection form. We can a topological E8 manifold, but these have no, so E8 has no smooth realization. So let's just E8 as 4 manifold. Maybe X but no smooth structure, and this requires low gauge theory. This actually using this is what you call even form, and have a spin structure, and then Dirac operator is, so this is what you call the loading theorem. If even the signature have to be moved, so then the signature in this case, because E8 is even, so the signature of this have to be 0, 1 below 16, and then here the signature is 8, so that's a rule out. But at least the Donaldson theorem, so that is Donaldson theorem tells us 2 copies of E8, or maybe X is topological 4 manifold with the intersection form 2E8 has no smooth structure. And then, but we have this what you call K3 surface, Palladian surface, which is -2 it doesn't really matter because this is the possibility, and then 3 copies of, and this is realized by S2 plus S2. So you can think that topologically, this K3 is homeomorphic to these some topological closed 2 copies E8 connection found with 3 copies of S2 plus S2. And now we can find the submanifold, closed submanifold, which is realize this part. What I'm going to write. Okay, so this actually just maybe jump which time. So from here that you're going to see that the inside K3 you can find some manifold with boundary, And this boundary, this manifold boundary essentially the second homology class just same as 3 copies S2 cross F2. And then the connect sum, here you have this S3 connect sum. And then so if this S3, from some, there's another way you can remove this, remove these 3 copies of S2 cross S2, and such that you can form here, you will get a topological homeomorphic R4 by remove certain 3 surgery, filling in this. And then this S3, which is a boundary here, and we cannot, this boundary, this is like a compact set. And this boundary, this compact set are not containing the standard S4. If you contain a standard S4, and then you can fill in, you will get a smooth. So basically, I'm just telling you that that is the exotic, this theory, the exotic R4, and is the field metal by something, which is probably the thesis work. And I think 82, the field metal is 86, sorry, at 2, at 3. And then even, of course, there's not straightforward. I don't think give a talk in, this is what the Peter told me. I don't think give a talk in Berkeley about long diagonalization theorem and Friedman, and then some of you casting all these, they immediately realized that they can do this. So essentially, and then come from Texas, find the second one, and then Tops find the infinite many and complement. So you all using this model space. Okay, so so you can see that the analysis put an important part in there are 2 theorems of Nuremberg, which one is put this connection with small curvature into Coulomb gauge. That is quite unusual. The second one is the remote similarity. Suppose you have AAT connection on a sphere with punctured sphere with a simple movement, and you can extend it to different bundle. To an ST connection with a bundle which extended to the center, and is the equivalent to gauge equivalent to away from the center. So these 2 theorems, of course, top theorem. So maybe you have more. Beginning, I have that one. Maybe I can just give you minutes. Just some generalization from the even generalization. So the word doesn't just connection. You have spinors, you have all other fields, connection in the one form, and so it turned out that these in 1994, Subwitting come out with a U1 gauge theory. But this U1 is coming from the spin C structure on S4, and then you have the Dirac operator. So we have a U1, I say U1 gauge theory, which is essentially U1 connection. Gauge field is essentially the U1 connection, and then you have spinor, and then you have U1 connection. So the dual part of U1 connection is some quadratic form of this. So this subintegration, which is simplified, like usually 2000 theorem in 50 pages, so 100 pages in subrouting theory, 1 page or 2. So it's straightforward. So simplification is and then of course Witten has this conjecture, and which is so we can say that the subrouting actually equivalent to Townsend. So in terms of how you need to writing the invariant by certain generating functions. And then next one, it come out Wang Witten. And here you have not only now again you have simple bundle over this S, they just take SU2 with the connection, and then you have actual form, and this form actually is a self-dual 2 form on this adjoint bundle. And then instead of the self-dual part is equal to 0, and is equal to some quadratic part, and then some coefficients, some quadratic form of this, of course, is quite unusual. But then, and then there's another equation, which is another equation is this is covariant. And of course, we have to move the gauge. And this is something to do with the physics. Actually, it's coming from here. and towards this solution they discover. And then maybe for the symplectic form manifold. Symplectic form manifold, and then again the topes prove that this can subrouting invariant you can define this Rhuaidi Burke. And this is by counting homomorphic Riemann surface inside this form manifold. And then I think that the Wafa and his is Rhuaidi Burke, which is just last year. Rhuaidi Burke and his the physics. There are some physics argument which again for symplectic form manifold, the Wafa within invariant equal to some invariant. And in the cell, what is the mathematics here? The mathematics here is with lack of compactness. So the more you have a sequence, you blow up singularities is co-division form in which just a few points. And there's a measure which is governed by the C2, the second chain class. But it turned out for the Wafa within, they don't have involved, their similarities could have like a one-dimensional cost of one. And then this is, then the even more remarkable probably is within. This is another generalization. And so this, maybe this is Wafa within equations. And the Witten claim that this is a real interpretation, real meaning of Jones polynomial for the nodes. But you would imagine that Witten got squared medal for the Jones polynomial, the interpretation of Jones polynomial. And he said he finally understands why it is true. Okay, so it's using for again it's form manifold, and now with a boundary, the boundary has three manifold. And this three manifold contain nodes. And these nodes, if you look at the level of length, this is S1 cross D2, this inside Y. And then inside, so you have nodes, and then you have so we can claim that you have counting with within equations with a particular boundary condition, which is called not the Lamb-Paul boundary condition. And counting this solution will give you the coefficients of Jones polynomial. Jones polynomial is defined differently, but we can have another topological field theory axiom derivation using conformal field theory. And now we can claim that this is the true meaning of this counting coefficient, the numerative meaning of the coefficients of Jones polynomial. Okay, so and again, what is the mathematical is again, can you have the Bloomberg type theorem in all these equations? And the subrouting is easier. Wafa weighting, Kakuzu weighting, the all these analysis of the sequence of solutions, what kind of limit, in particular the limiter, the singular set, where for example the curvature blow up at certain points maybe, and then because you have actual fluid fields, this, for example, these fields, and some other, they also signal fields in the couple simulating, we also have some field which is kind of look like a gauge group, the argument part of gauge group, but actually it's some other fields and also some other fields from the field here. And the energy blow up could not just concentrate points, could be coordination 1, coordination 2. So and then you also can have high dimension mirror theory, which is just a pure gauge theory, you have similarity which is coordination 4. And that maybe some of you can look at this set of equations, you can look at the asymptotics or the limiter with the limiter solutions, what it look like. But maybe just give one minute. So you can this is 4D as the connections. But if you look at on Y, which is three-dimensional form R, so this is one compact. But you can put this connection in terms of temporary gauge called T. So it's a connection on Y, and then the T part is 0. This is 0. And then the ASE connection equation is same as the gradient flow equations for the transparent function on the space of connections on Y. And with the limit, if you look at the two limit solutions, ASD connections, and you can define homology of infinite flow homology. And that's called the 3D transparent theory. You can there often people study just the PDE of the from transparent theory and the import theory from New England and from Taiwan. There's group of study even abelian transparent theory. So what about if we have 2D? So you can see that the limit of this limiter is a connection on Y, and this actually is flat. And flat connection connect from the one to the data fundamental. So that's another way of constantly which and you can continue on to the 2D of their theory, and then again we just the flat connections. And so okay, so this is so this can think that now you have just someone asked me about what I'm doing, which is the 2D sympathetic vortex. This again is a set of equations which is a two-dimensional surface, and you have principal bundle which is a 2 bundle with a connection, and of course if the connection is flat, then you can do. But now there's a group company group, and you act on some another. So this will be a symplectic and manifold, manifold. Symplectic in a Hamiltonian way. And then there is a moment map, and leads to the Rhuadi Burke or dual Rhuadi Burke and Rhuadi Burke. And they can another set of equations, which is you can associate a bundle. We have another bundle which is P associated with symplectic vibration. We have this section. Maybe choose the complex structure, and if you choose almost complex structure. Suppose the Keller that choose complex structure, and they want this section. This section use the connection. You can horizontal and vertical. Horizontal have even surface complex structure. And the vertical you have a Keller or symplectic. They have a almost complex structure, and these have complex structure. And you require that this is homomorphic sections. And then the second equation, instead of curvature is level, and curvature is just applying moment map. And again, modulo this. So this is what I'm doing at the moment. And for the future, I would like to, instead of gauging everything, you can think that this is something to gauge going to theory. What we often people in physics call gravitating gauge theory. So on the gravitating Young-Miller theory. So okay, so here is pure. So we have this.
So, right, I think we need to wrap up.
Yeah. So okay, so I'm saying that suppose you have an equation coming from general relativity, say even rich flow. You have model space and rich flow. What is the study of this? So actually, I probably asked them 10 or 15 years ago. Anyway, so this. I will be glad to announce this work and solve the problem. At the moment, the people couldn't study and make more progress because we don't have more here and more. Okay, thank you.
Thank you very much. I didn't give you a proper introduction, but this was Bai-Ling Wang, Brian. And thank you indeed to all of our speakers for introducing us to the exciting things that we might expect to see in Yang-Mills theory as we continue studying this year. I think we'll wrap up there. So thank you for those of us who joined us on Zoom in particular. Thank you all. I hope you enjoyed this. And special thanks to all of you who made this that UNSW today. So thanks to all of our speakers throughout the day, and I hope you had a pleasant time.
Thanks to the team for organizing.
Yeah. Thank you, everyone.